This video is going to cover a proof of why certain values of equilibrium from discrete systems, namely the eigenvalues of a system Jacobian matrix evaluate the equilibrium, why we want those eigenvalues to be less than 1 in absolute values, or the real part less than 1 in absolute values to lead to stability. So we're going to consider a discrete equation. So in this case, we'll consider two discrete equations, but really in a moment, we're going to extend this to such generality that this could be any number of coupled discrete equations. We'll assume that there's an equilibrium point, so we have all of our x bar, y bar, z bar, whatever friends we need if we're considering a general system. But for right now, we can think of this just as a two-coupled system of equations. And we're going to actually go through the proof of why a Jacobian's eigenvalues really tell us about the stability properties for a specific equilibrium. So if you've watched the previous video for single discrete equations, we're going to follow much of the same steps, except the first step will be new. We're going to put our system into a vector format. And this is just going to be a helpful notation for us that's actually going to help us reflect a lot of what we've already done for that single discrete equation case prior. Then we're going to define an error term just like we did before. We're going to Taylor expand something. We're going to cancel out some terms and truncate that Taylor series. And then finally, the last step, we get to solve a first order discrete system in a very much a similar flavor of what we did for that single discrete equation proof case prior. We're going to see that this last step, though, we're going to get to pull in a few more mathematical tools from linear algebra. But this is sort of our guide for how we're going to approach this proof. So let's go ahead and first put everything into vector format. So there was our system that we previously considered. So I'll put a 1. So in terms of the vector form. And all we're going to do is basically say, you know what, instead of considering each equation individually, I'm going to define a big old vector that looks like this. Some fancy x of n plus 1. And what this will actually be will just contain both of those elements, xn plus 1 and yn plus 1. So in much of the same way, we could define our previous value, iteration values, in the similar kind of vector sense, just denoted by that subscript n. So why are we doing that? We're going to do that because now, if we use this vector format, we're not as restricted to actually knowing how many components are in that vector right now. We can think of this as though we're just solving doing this for two coupled equations, but really when we do this in a couple moments, it'll extend to any number of coupled discrete equations. So we'll define those two quantities. The other thing that we're going to define is a function g that's itself going to be a vector function. And it's going to be a vector function of our iteration values. So you might see where we're going with this. We're basically going to put our functions f and g up above into a vector as well. And if you want, this notation actually extends inside of those vector functions, or inside those individual component functions. Since those component functions, f and g, depend on all of those values, xn, yn, etc., we could write that very compactly in a vector notation. But just so we're all on the same page, what that really means is we're really saying, you know what we need is f of xn, yn, etc. Just to show you how we can vectorize this entire system. So if we write down our equations, what we actually have now is this iterative looking vector discrete system, where our next iteration values in this compact vector format is equal to, well, that vector function g of our previous iterative values. So you can see how this looks very, very familiar to maybe the form that we did for single equations. So just a quick aside, where we had things like single equations are zn plus 1 equals some number, say times zn. This looks somewhat similar, or sorry, doesn't have to be that restrictive, but if we have zn plus 1 is equal to some function of the previous iteration values, something like this. All right, and the reason we're going to do that, this compact vector format notation, will actually help us basically do the Taylor expansions and all of that jazz in very much an analogous way to what we did for single equations that look very familiar to this down here. As a spoiler, we're going to get to pull in some calculus C, or multivariable calculus tools to help us out. So let me just get rid of this, just so we know what we're solving. So the second thing we get to do is to define that error term. And when we talk about this error term, we are still talking about the difference now between the equilibrium point and our iterative values. But since we have multiple iterative values, just like we have x bars, y bars, we define a vector error function to be the difference between our vector of iterative values and that equilibrium point that I guess we'll define in a second, but this is going to be x bar equilibrium point. So just so we're on the same page, x bar equilibrium point vector is actually just equal to x bar and y bar in a vector format. So many bars, so many vector signs. All right, so let's go ahead. If we iterate this again, the next iterative distance between our values is just, well, vector xn plus 1 minus that equilibrium vector. So we're going to go ahead and start Taylor expanding in a moment. But as you noticed from before, we can do similar type ideas. Namely, we can solve for our xn iteration vector in terms of that error and our equilibrium values. And in fact, let's start to just confuse ourselves because we have lots of x's, lots of x bars, things like that. Let's actually start calling those values that we're calling the equilibrium. Let's call that actually, say, alpha vector. So at least we have something that looks different now. So again, this is our new vector of equilibrium values. So I'll lasso this and bring this to the next page. And let's start moving towards a Taylor series expansion. And the way in which we're going to do this is I'm going to first just remind us that we can solve again. We can solve for the xn vector in terms of our equilibrium values plus that error term, or the distance between our successive iteration values and the equilibrium. And then we're going to go ahead and take our next iterative error value, en plus 1, and we're going to start substituting in what we know some quantities to be. So remember, what we called this was actually equal to our iterative function of how we're getting to the next iteration values. So similar as before, if you flip back a page, this is just equal to our iterative function, g, evaluated at the previous iteration values. And the next thing we can actually do is go ahead and substitute in what we know xn vector to be in terms of the equilibrium point and the distance we are away from that point. So we're going to go ahead and substitute that in next. So our next error term can be written in terms of our iterative function g evaluated at our equilibrium point, alpha vector, plus the previous error term, E sub n. And this is the statement that we're going to get to Taylor expand in a moment. And just so we're clear, the reason why is we're evaluating this vector function g at the equilibrium, but then we're not exactly evaluating at the equilibrium. We're some small distance away. So again, just to remind us, we assume that E sub n is small. So all of the components of E sub n we're assuming are small, very much in the same way we assume that the error term for a single discrete equation was small. This is where we get to pull in the tools of rigorous real analysis to actually help us out here, where we start defining epsilon neighborhoods around the equilibrium point and so on. But for us here, let's just go ahead and start Taylor expanding. And the really groovy thing about this is the Taylor expansion we're going to do is a multi-valued or multivariable Taylor expansion. So let's check out what this looks like. And if you're unfamiliar with what this looks like, that is a-okay. Just keep in mind, this is a Taylor series after all. The first term is just the function evaluated at a quantity. The second term is some derivative related thing. The next term is some second derivative related thing. Third term is the next term after that is a third derivative related thing, fourth derivative, fifth derivative, things of that nature. It's just that since we are now in the world of multi-valued functions, these of course are going to be first partial derivatives, second partial derivatives, third partial derivatives, and so on. So let's check this out. So the first thing we do, we expand that into Taylor series, we just get to evaluate our function at that equilibrium point. The next thing we do is take the first partial derivatives of that vector function. And now, this isn't as easy as it may seem, but what we actually do is apply what's the equivalent of a first derivative operator in these multi-valued sense, which is our gradient operator. And we apply the gradient directly onto our function g, evaluated at that evaluated at that equilibrium point. And then we do a multiplication, which in this sense is a dot product or a vector multiplication with our error vector E sub n. We're going to come back and talk about each of these terms, but remember this term is really just our first derivative term. But these are first partial derivatives now. The second term we get, and this might look a little funky, is the following. We have that 1 over 2 factorial coming from our Taylor series. We have the transpose of our error vector being multiplied onto, well, if we want two derivatives for partial derivative settings, we have gradient of the gradient of our function g that will eventually evaluate at that equilibrium point. But we're not done yet because we multiply that quantity onto our error vector. And we would get many more terms in the Taylor expansion. But I'll save you from those. We'll just do the plus ... But we have to remember that we get to subtract off our equilibrium point at the end. Okay. And maybe it's good to know that this whole thing over here is still some second derivative term. This is actually called a Hessian matrix when you do it out. But for us, let's not focus on that detail right now. The other terms are what we're going to actually use. So I'm going to pull this to the next page. And let's go through some of these terms individually. Actually, if I'm lassoing it, let's just set this up better for the page. So let's take a look at this first term, or the second term in the Taylor series, I should say. This gradient of our vector function g. What this actually turns out to be is this turns out to be our Jacobian matrix. This would have been our vector, so if we write this another way, the gradient of this vector valued function is something that we typically just call our Jacobian j, but in terms of our example that we're using, the two equation system, what this actually turns out to be is a partial derivative of our function f with respect to x, partial derivative of our function f with respect to y, in the first row. In the second row, partial derivative of g with respect to x, and partial derivative of g with respect to y. In the language of our two-coupled equation before. But this is really just some matrix that we're getting. So let's just rewrite what we have then in terms of that matrix. So we still have our iterative function g, that's a vector function, evaluated at our equilibrium point, plus that Jacobian matrix now, j, evaluated at our equilibrium point, multiplying onto the vector of errors E sub n, plus that lovely, complicated-looking second derivative term that's actually known as our Hessian matrix. All right, the next thing we're going to do is focus on this first term, because we notice that this first term is evaluated at that equilibrium. And remember, that is our iterative term, how we're actually getting to the next function. We already defined, remember, that our iterative vector function, xn plus 1, is equal to that function g evaluated at the previous iterative vector. So if we're sitting at an equilibrium point, what we actually have when we evaluate that function g at our equilibrium vector, the vector of all our equilibrium points, well, that should just return the equilibrium points back. So we can actually substitute in, you may have guessed that, our vector alpha. So let's go ahead and substitute in alpha. And you might see the reason for that. We're going to be able to cancel those two alpha quantities. So you may be noticing a similar trend to what we're actually doing for this multi-valued case and the single equation case. We're able to cancel out that equilibrium point from our Taylor expansion. And then we're just going to get that the next vector of distances from our equilibrium is equal to, well, this Jacobian matrix evaluated our equilibrium times that distance vector at the previous term plus all those higher order Taylor series terms. So let's pull this Taylor expansion, or what's left of our Taylor expansion, to the next page. I guess for labeling purposes, when we started canceling things, I should have put a 4 up here for our fourth step. But either way, we're getting towards what is left in this Taylor expansion. And this is where we get to focus in on these E sub n quantities. And to motivate this idea, what's actually going to happen, since we have, for example, En transpose and En, we're going to get a lot of multiplication terms involving the first component times the first component of that error vector, first component, second component, and whatever have you, all the cross terms, all the square terms. So over here, we're going to see lots of second order power or second powers. Or nonlinear powers where the total exponent is equal to 2. Basically, what we're driving at now is just like what we said. We're assuming that all the quantities are small. All components in this vector are small. So if we start having vector value components being multiplied against each other, for example, E sub 1 squared. So let's just actually make this a little more explicit. If we write out our error value vector, this would be like the first component of that vector, the second component of that vector, etc. We're going to start seeing that terms like E sub 1n must be a lot larger than things like E sub 1, that first component again, but squared. Just like what we did for our single equation case. Or we'll see that E sub n1 still must be much larger than the product of the first component of that error vector and the second component of that error vector. Basically because, so again, I want to emphasize that when we have kind of the total power of 2 on that right-hand side versus multiplying a couple of these components together, having just these single things on the left-hand side must be a lot larger because we're assuming that all these components are small. So multiplying any of these components together or squaring these components will result in something much smaller than just the original thing. So because of that, we're actually going to be able to just more or less cancel a lot of these terms. In fact, all of these terms on the right-hand side except for the first one. And this is very similar to what we did in the single discrete equation case, where we got rid of all those higher order Taylor series terms except for that first term with the derivative, or the first derivative term. It's just that in this case, our first derivatives are all partial derivatives inside of this Jacobian matrix. So at this junction, we now get to solve this equation. so we can see how the error propagates. Does it get larger? Does it get smaller? So this is where we're going to actually do a lot more linear algebra, believe it or not. So I want to emphasize a couple things before we get into this. We are driving towards why are eigenvalues important? Where are those ideas coming from? As well as why do we want eigenvalues to be less than 1 in absolute values, or real part less than 1 in absolute values? So keep in mind, that is where this train is going. We're going to get eigenvalues at some point, and conditions on those eigenvalues. So let's dive into it. And the first thing I want us to recognize from this is, for example, if we start off with E1 vector, well, that's just going to be equal to our Jacobian evaluated at the equilibrium point times whatever the original error is. And just for shorthand, we're going to still consider evaluating that Jacobian at the equilibrium, but I'm just going to call that J for now. So if we looked at E2, for example, well, that's just going to be J times E1. But we already know what E1 is. We know that E1 is actually just J times E0. So if we substitute this in, we'll get J times J of E0. Or in other words, we get J squared, the Jacobian squared, times our original error vector. If we did that for the third term, we would find out that by doing the same iteration process, we get Jacobian cubed times the original error vector. And we could keep doing that. And in fact, if we kept doing that, what we would eventually see is that the n plus first error is actually equal to J raised to the power of n plus 1 times the original error vector. So all that to say, what it looks like when we're actually iterating this discrete equation is we are just multiplying this Jacobian vector onto the original error vector over and over and over. So that's the first idea I want to bring us into. And in fact, maybe we shouldn't have jumped to the n plus first. So what I want us to take away from that is, if we have our vector iteration set up as the next value is equal to our Jacobian times the previous value, that the nth vector, error vector, is actually just going to equal then our Jacobian raised to the power of n times the original error. So this is going to be the takeaway from that previous. Now, this hasn't solved our thing yet at all, but what it showed us is we need powers of the Jacobian. That's going to be important. The second thing I want us to do, and this is where we're actually going to talk about eigenvalues. Is if we have a matrix J, we can actually do a diagonalization or a factorization of this matrix in terms of its eigenvalues and eigenvectors. So, for example, in this case, what we actually do is we can expand this in the following manner. We can write this in terms of a vector v times a vector of capital lambda times a vector inverse of v. So let's define these things. But this is, again, a matrix diagonalization. This vector of capital lambda is just equal to a diagonal matrix where along the diagonal are all the eigenvalues. Everywhere else in this matrix are zeros. So the only non-zero thing is actually just along the main diagonal. This matrix V is a matrix where every single column in the matrix is a different eigenvector. So each of these columns are a particular eigenvector that corresponds to a particular eigenvalue. So hopefully you've seen this before in a linear algebra course. We can rewrite our Jacobian matrix, and again, this is our Jacobian evaluated at a specific equilibrium value. Let me just make sure that is clear. In terms of this diagonalization on the right-hand side. So let's see what actually happens when we put these two ideas together. And just so we're clear, this matrix in the middle of capital lambda, this is where the eigenvalues are coming into play here. But next thing we're going to do is combine these two ideas of what's going to keep happening to that right-hand side if we keep multiplying by that Jacobian over and over. So let's grab those two things and go to the next page. So at this junction, we know that the nth error is just equal to the Jacobian raised to the nth power times the original error term. And we've also defined that the Jacobian evaluated our equilibrium point could be written in the following matrix factorization, where again, this matrix in the middle is a diagonal matrix whose entries are all of the eigenvalues. So let's take a look at what happens. For example, let's go back through our iterative process. If we have E sub 1, that is equal to j times E sub 0. Substituting in what we have now, that is V times capital lambda, V inverse times E0. All right, nothing too fancy. However, E2 we saw was equal to the Jacobian squared times the original error vector. So what that equals on the right-hand side, V capital lambda, V inverse, times V capital lambda, V inverse, E sub 0. And well, let's see what actually happens when we continue multiplying this out. Well, we'll still be stuck with that V on the left-hand side. We'll get a lambda, we have a V inverse, we have a V, we have a lambda, we have a V inverse, and finally we get that E sub 0. And well, if we notice what's happening in the middle, we have V inverse times V. This just gives us an identity matrix. So this actually substitutes rather nicely for us. It becomes V capital lambda, V inverse, E sub 0. And well, what we have now is just, well, for multiplying lambda against lambda, this is just lambda squared. So all of a sudden this now becomes V lambda squared, V inverse, E0. And the interesting thing that you can actually show yourself is if we kept doing this process, so if we looked for E3, which is just the Jacobian to the third power times E0, what that actually gives us would be V lambda to the third power, V inverse, E0. And we could keep doing that, but eventually, like we have up here, if we're interested in that nth iteration, we have E sub n is now equal to, well, the Jacobian to the nth power times E0. But what we see by substituting in that factorization is we're just going to get a V matrix of eigenvectors, times our diagonal matrix of eigenvalues raised to the nth power times V inverse E0. So when it looks like we're raising that Jacobian to the power of n, we're really just raising this eigenvalue diagonal matrix to the power of n. So let's actually take a look and investigate this. And at this junction, we are very close to finishing off this proof now. So we could equivalently write this thing on the right-hand side as our matrix V. That's just some eigenvector matrix. But then if we wrote what that matrix lambda is, well, that's lambda 1, lambda 2, if we just had our two coupled equations. But if we have n coupled equations, we have n eigenvalues. We raise that matrix to the power n. We multiply it by V inverse, the inverse of our eigenvector matrix, and then multiply that onto E0. And now what's nice is if we take an diagonal matrix and we keep multiplying that diagonal matrix against each other, the only thing that's going to change is we raise those diagonal entries to that power. And again, this only works because it's a diagonal matrix, but on those powers, we just now have each of those individual eigenvalues being raised to the power of n. And just so we're clear, maybe I'll say there are m eigenvalues now, if we have m coupled equations. We have lots of n's going on. If we just had our two coupled equation case, we would just have lambda 1 and lambda 2. All right, well, let's take a look at what's actually happening then. So just to clarify, we have our distance vector at the nth step. This is the distance between our equilibrium points and each of those iteration values. We're able to write it as some constant eigenvector matrix times another diagonal matrix, where all those things in the diagonal matrix are being raised to the nth power, times some other constant matrix, this time just the inverse of our eigenvector matrix, times the first error vector, the first distance between our iteration values and equilibrium points. And well, what we want to investigate is what's going to happen to this matrix as n increases. As in, what's going to keep happening as we keep iterating? And well, what we see is if lambda j is less than 1, for all j, this matrix looks like it's going to 0. And again, just so we're clear, this could be either if that absolute value of each eigenvalue is less than 1, or the absolute value of just the real part of that eigenvalue is less than 1. This will happen. Those eigenvalues raised to the nth power as n gets larger and larger, if either they are less than 1 in absolute values or their real part's less than 1 in absolute values, as we keep raising them to the nth power, they're going to get smaller and smaller and smaller and smaller. And eventually, as n goes to infinity, that matrix is going to look just like 0. If that matrix looks like 0, what it says is, well, then the distance between our iteration values and the equilibrium looks like they are also going to 0. And this, in very much spirit, is the proof of this case. The only thing we didn't do rigorously is really talk about what we mean by being close enough to the equilibrium point, or starting to define those epsilon neighborhoods around the equilibrium point to actually talk about what we mean by close. But this, in very much spirit, is the proof of why we want those eigenvalues to have certain restrictions for stability.